Welcome to the second half of lecture 17, scheduled for the end of week 6 in our 8-week summer course on computer algorithms. So we are closing off the chapter on network flow in our textbook or on iterative algorithms, and we consider one last application, that on airline scheduling. We will see that this problem can be solved efficiently, and this is a good thing because we all like to travel in summer. So what's the problem? We want to assign airplanes to flights. So we have P airplanes and we want to serve K flights. The short question is that sufficient to have that many airplanes? So every flight is given by an origin and a destination airport and a departure and arrival time. So um, we have a number of flights. So the same plane can actually serve different flights. Um, but there should be enough time between the departure time of the second flight and the arrival time of the first flight. And uh, that's one thing. And it could also happen, so that's the time constraint. It may happen that the destination of the previous flight is not the same as the origin, so that the we're considering two flights and they not only have different times, but they actually also do have different uh, origins and destinations. So then we have to take that into account. So we have to take into account that there is additional time necessary to fly from the destination of the ith flight to the uh, origin airport of the next flight, J. Okay, so here is a very simple example. So we have a number of airports, and in one day we have to serve 6 flights. The flights are given by these arrows here. So it starts at 6 o'clock from a flight from Boston to Washington, D.C., and it ends with one last flight from 4 o'clock till 5 o'clock. And you can see that some of the flights are starting when the other one ends. So obviously you need at least 2 airplanes because a plane cannot instantaneously at 7 o'clock go from Washington, D.C. to Philadelphia. So DCA here to this um, airport here. Now, the question is at least 2. Will you need more than 2? Okay, so I can give the solution right away. So here is the solution. So there are 2 planes, one red and one uh, blue. The fat arrows indicate the travel time for a plane to go to the next flight, going from the previous flight that had a different destination to the next flight that had a different origin as that destination of the previous flight. So yes, 2 airplanes can do this. Let's solve this problem um, in general, because obviously airplanes have way more than 2 airplanes and they serve way more than 6 flights on a day. So this problem has to be solved efficiently. Um, here are here is a graph which defines all reachable flights and in some sense defines all possible solutions. So in our solution, we send the top graph, the top flight here to the next top arrow, but we could also have had that plane travel to serve another flight. So the graph that will be working with will actually contain all the information of all the possible uh, assignments that can be done. Okay, so let's now formalize this. So we say that a flight J is reachable from I. It is possible to use the same plane for the first flight and then also later for the Jth flight. Okay, so then our problem is specified by the number P, the number of planes, and then for the K flights, we have the origin and destination airports and the departure and arrival time. And we also have the edges in our graph. So the vertices are the origins and destinations. So in some sense, this is a two-dimensional problem. Every vertex has coordinates in time and in space. So it's a feasibility problem. So it will also be formulated as a circulation problem. So does feasible circulation in a flow network exist? So how are we going to define our flow network? So the flow network is the input to the Ford-Fulkerson algorithm. So we will represent that flow network by a set of vertices and edges. So every flight is represented by two vertices, its origin and its destination. And then we have the flight that we must serve. So we have a lower bound that equals the upper bound. On the edge between the origin and the destination. So a flight is reachable. If a flight actually is reachable, then we indicate that there is this edge from the ith vertex to the jth vertex, and we have a capacity of 1 there and a lower bound of 0. So in some sense, we have the flights that we absolutely must serve. There you see the purpose of the lower bounds. Also, one plane suffices. The capacity is 1. But then there are in the edges, in the reachable graph, we have the edges for which we have optional paths. So where we have capacity 1, but the lower bound is 0. Okay, we have to add a source and a sink. So this will be translated in a circulation with demands and lower bounds. That's a problem that we discussed in the previous lecture. So we have a demand of minus P. Minus demand means actually supply. So at our source, we have our P planes. And we want that all the planes arrive safely at the sink. So all the other vertices in this network are internal nodes, so they have demand 0. So in every flight is now represented by an edge where we have capacity 1. So connecting the source with the origin airports and connecting the destination to the sink. So one airplane can optionally then directly fly after done one flight immediately to the sink of our flow network. So we can incorporate extra planes. So in order to have this make a circulation, so we need to have that we don't lose any planes. So what we have a demand of negative P, but you could also not use certain planes. So there's nothing that says that you have to use all planes. So you have an extra edge that goes from source to sink with capacity P. So that means that you have some extra planes that will travel from source to sink without serving anything. Okay, so this is the flow network. So the question is always if you can solve a problem in polynomial time, you have to formulate the input also in polynomial time. So that's an additional exercise. Um, so we would like to solve this problem from the beginning systematically. So we look at that problem for we have already the solution. So in some sense, it's not a matter anymore to run the algorithm, but how can you argue that this is really the optimal solution? So the Ford-Fulkerson algorithm terminated when there was no path from source to sink in our residual graph. Can you use this justification also here? And what does optimal really mean in this sense? Because you do mean the optimality still makes sense from the max flow problem, but for the feasibility question, what does it mean there? It relates to the termination of the algorithm. Okay, we have a scheduling problem, and for the scheduling problem, we defined a flow network for which we can compute flow. Now, that doesn't necessarily mean that the flow is meaningful to the scheduling problem. And in the other way around, what does it really mean if we have a schedule? Does that map into a feasible circulation? Okay, it's an if and only if. So we have, if going from left to right, we actually do have um, that P planes that suffice to schedule to serve the K flights. So at most P planes, so we would have P prime, possibly less. So every plane defines a path. So it's a little bit similar to the problem we started with at the beginning. We would consider paths in a graph. So with every path, we can send actually one unit of flow. And since the internal nodes all have demands 0, so and the flow preserves, so a plane that comes in leaves, that's also one way to see this at the internal nodes. So we send in that much flow, and we have uh, a circulation which satisfies the demand, the capacity, and the lower bound conditions. Okay, if we can serve K flights with at most P planes, we do have circulation. If we have circulation, do we also then have a schedule? Do we actually know that we can, that P planes will suffice? Okay, so how are we going to do this here? So we're going to interpret the feasible circulation. It gives us integer values. Now, the capacities on the edges were either 0 or 1. Actually, the capacities were at most 1, and the lower bounds were either 1 or 0. So, getting the circulation, can we compute the paths? Well, if there are edges of flow, then we are adding it to the path. So for every circulation where we have a flow of 1, we consider where the plane departs from the source and where it gets to the origin, an origin airport, and then by conservation it would need to go to either directly the sink, uh, but probably not. It will go to the destination airport, and then we will continue that path to the sink. So in some sense, this is a little bit similar to the edge disjoint path problem from the beginning of this lecture, but obviously we do not have cycles here because we have a strict progression, a strict direction from origin to um, destination airports, um, and a strict time from source to sink. I think that is the main constraint here. Okay, although I think we might have cycles during the day if we go back morning flight, noon flight, and then evening flight. So you could potentially have cycles there. But in any case, the point is that we can, from a circulation, we can do the paths. And that means that if we have a flow of that many units, then we have that many paths. And we can serve that many flights. Okay, I have to stretch things a little bit because the presentation went rather fast. So if we have a number of P planes and K flights, what is now the cost of solving this airline scheduling problem? We know that the scheduling, the feasibility for the circulations with lower bounds can be translated into a circulation problem with demands and 0 lower bounds or no lower bounds. Um, and from that, we can solve this with the Ford-Fulkerson algorithm, which runs in times the number of edges times the cost bound. Okay, so we start with P planes, K flights, so we have at least K edges, but in our flow network, we actually start also from the graph of reachable flights. So you can assume that the cost in function of the input is that capital M, the number of edges in the graph of reachable flights. That's the M, where the graph of reachable flights is extended to a flow network. So we're going to add a source and a sink where we have the origin airport. So every origin airport in that graph will be connected to the sink, and every destination airport will also be connected to the sink. So we have the source and the sink that are added. We have a number of flights, so we have K flights, so we're going to add 2K extra edges on top of the M. So your answer should actually contain the M plus K. Okay, then comes the key. We have the cost bound. And the cost bound actually was bounded by the optimum value, the maximum flow. But here actually we have an upper bound already, and that is the P. So the if you can find a maximum flow of P, then your P planes that start from the source will actually also end at the sink, and they will have served all the K flights if the circulation was feasible. Um, so therefore, we do have a strongly polynomial time algorithm. So another way, and actually a much shorter way of saying this, is that the capacities were all 1 and the lower bounds were 0 or 1. Um, okay, so this concludes this lecture. Also, it concludes the entire chapter on network flow, where we considered iterative algorithms. So the Ford-Fulkerson algorithm proceeds in multiple stages, augmenting the flow. Um, it's not always obvious then that iterative algorithms terminate, but it was very important that in this course we study only discrete problems and we computed discrete numbers. So everything was discrete, the flow was discrete, the input is discrete. Nevertheless, the size of the numbers mattered. For some problems it did, for other problems it didn't. If it didn't matter, we had strongly polynomial time algorithms. If it did matter, we had pseudo polynomial algorithms. So we have covered, after the treatment of the Ford-Fulkerson algorithm in lecture 15, we've covered 5 different problems. And here is the listing of the problem. For some of the problems, we do have a strongly polynomial time, like for the edge disjoint paths problem. We didn't have this anymore for the customer survey design, and also we do have then again a strongly polynomial time algorithm for the airlines scheduling. Largest matching was also strongly polynomial. Circulation with demands was pseudo polynomial. So this is an interesting connection between the problems, the examples that we have covered, examples of problems that can be reduced to the maximum flow problem. So I hope this lecture was not too confusing. It's harder to make it self-contained because it depends on lecture 15 on the Ford-Fulkerson algorithm, and actually the circulations were already covered in lecture 16. In the next lectures, we're going to introduce also reductions of problems, but there we're going to have reductions to problems for which there is no polynomial time algorithm. So that then means that if you would be able to show that you have a new problem and you can reduce it to a problem for which you can say that's equivalent to a problem for which there is no polynomial time algorithm, that will also be very important information. So here in this chapter 7 on network flow, we did polynomial time reductions to a polynomial time algorithm. In the next set of lectures, we will also do polynomial time reductions, but then to problems for which there is no polynomial time algorithm anymore.